Previously, we introduced the idea of a sequence as basically being a function of the kind that we're used to, with the proviso that it's only legal to plug positive whole numbers into the function. So, for example, rather than writing a of n equals, we'll write a with the index downstairs, pronounced a sub n. For this particular sequence, this will be n over n plus 1. So a sub 1 ends up being 1/2, a sub 2 ends up being 2/3, a sub 3 ends up being 3/4, a number 1000 would be 1000 divided by 1001. It should be clear that all of these numbers are positive, and as I allow the index to increase, these numbers, even though they're all less than 1, get close to 1. Sometimes when you're dealing with the limit of such things, as we allow the n to become indefinitely big, you can sometimes just do algebra trickery on it. Sometimes we can just do algebra trickery on a problem of this nature. N over n plus 1 can be written as, in the numerator, n times 1, and in the denominator, write this as n multiplied by 1 plus 1 over n. The top and bottom of my fraction are polynomial expressions in terms of n. They have the same power, so I can cancel the n out. As n becomes very large, 1 over n becomes close to 0. 1 plus 1 over n gets close to 1. The fraction that I'm looking at is a fraction with a 1 upstairs and a number downstairs that's getting very close to 1. The limit is 1 over 1, which is 1. We shouldn't say that the limit approaches 1. The limit is 1. The numbers n over n plus 1 approach 1. Now, previously we had talked about the epsilon definition for limits. I've decided that in view of the amount of time that it would take to backtrack, I'm going to treat that very lightly as we go along, but I do want to look at one particular example. I want to look at this one. The definition of a limit, in particular, the limit as n goes to infinity, n over n plus 1, to equal 1. What that means is, if you give me a positive number, which I'll call epsilon, then given that positive number epsilon, there is an index that I'm going to call capital N, so that the following thing happens. If you give me an index that's bigger than this particular index, capital N, then the difference between the numbers of my sequence and the thing that I'm alleging is the limit can be made smaller than this number epsilon, just by virtue of the index little n being large enough. Now, to look at this exactly, I'm going to look at the thing that I want to control. I'm going to look at this absolute value, and I'm going to ask myself, what does it mean for this quantity to be less than epsilon? Now, this is what I don't want to happen. I don't want to see that it's true for a certain stretch of n values, and then untrue for another stretch, and then true for another stretch, and so on. What I want to see is there's some particular capital N beyond which this will always be true. If you do some algebra, 1 is n plus 1 over n plus 1, so I can write the thing inside the absolute value as a single fraction. the absolute value of -1 is 1. The absolute value of n plus 1 is n plus 1. So if I can find some particular index, capital N, so that when little n is larger than that particular index, this happens, then we will have proven by the definition that the limit actually is 1. To see when this happens, I'll just solve an inequality. Remember that you can multiply both sides of an inequality and divide both sides by positive quantities, and it doesn't change the inequality symbol. So taking the thing that I'm interested in having happen, multiply both sides by the positive number n plus 1, divide both sides by the positive number epsilon, then I can subtract the same number from both sides of the inequality. What I want to be true is going to be true when 1 over epsilon minus 1 is less than the index on my sequence term. That is to say, when the index is bigger than 1 over epsilon minus 1. Epsilon is just a positive number. It doesn't have to be a whole number. But if you give me a positive number, epsilon, big, small, whole number, not whole number, then 1 over epsilon will be a positive number. Subtract 1 from that. If my index on the individual sequence terms is bigger than this number, then things will work out the way I want them to work out. So the capital N will be a positive integer that's bigger than 1 over epsilon minus 1. So we have demonstrated the existence of the capital N that will make the difference between n over n plus 1 and 1 less than epsilon in absolute value. This proves that the limit is equal to 1 by this logical definition. Those who are interested should read through the section in the Calc 1 book about this, and you'll see that this type of manipulation becomes very tricky very quickly. One problem with these sequence functions is that in a certain sense there are many techniques from Calc 1 that I would like to use on them, but I can't. For example, I'd like to do L'Hopital's rule on some of these things, but I can't do it because my sequence functions are only determined at specific, well-separated n values. I don't have a continuum of x values like we did back in Calc 1. One way to get around this, at least partially, is what I'm going to call an f of x trick. We may have several of these as we go along. Suppose that you had a function f that was defined on the real line, not just at positive whole numbers, just any old numbers. Suppose that you rigged this function up so that if you were to stick a positive whole number into it, you would get the corresponding sequence term. If the limit as x tends to infinity of f of x is some number L, then the limit as n tends to infinity of an is also equal to L. The reason for this is not very difficult to see. If the limit as x tends to infinity of f of x is L, this means as I allow the x-coordinate to get large, the y-coordinate has to get close to L, either from above or below. So given an x value, if I make the f of x large enough, misstatement. If I make the x large enough, the f of x has to approach L, meaning that the y-coordinate on my graph has to get close to L as well. This is true for all x's that are big, in particular the x's that we're really interested in. If I pick the positive whole number 2, the y-coordinate on the graph will be f of 2, but we're using a function f so that f of a whole number is a indexed with that whole number. So this y-coordinate will be a number 2. If I evaluate f when x is 3, I get f of 3, but f of 3 is a number 3, which is closer to L, because for any x, as I let the x get larger, the f of x value is supposed to approach L. If x is the positive whole number 10, f of x, which is f of 10, is also a number 10, which is very close to L. Because all of the f of x's, as x become large, approach L, in particular, if x is a large positive number, f of x will be L, but such an f of x is an a number for some large index. I want to go back and look at the limit as n tends to infinity of n over n plus 1. The individual a_n's are n over n plus 1. The f function is going to be f of x equals x over x plus 1. Instead of looking at the limit as n tends to infinity of a_n, I'm going to look at the limit as x tends to infinity of f of x. On one level, this seems extremely silly. It looks like I'm just rewriting the same thing again, except using a different letter, using x instead of n, but that's not what's going on here. The a_n's only make sense when n is 1 or 2 or 3 or so on. I can't take derivatives of things like that. The f of x makes sense on a continuum on the entire number line, well, except for x equals -1, but since x is going to be tending to infinity, we don't worry about that. The difference is I can pull out all of my techniques from Calculus 1 to do this second limit. In particular, I can do L'Hopital's rule. The limit that I'm looking at is an indeterminate form of type infinity over infinity, and L'Hopital's rule says, write this thing down again, except take the derivative of the top, also take the derivative of the bottom. However the limit that I'm looking at right now acts, this new limit will act the same way, including converging to the same value if it converges. The derivative of x is x. The derivative of x plus 1 is 1 plus 0. The thing that I'm taking the limit of doesn't actually depend on x anymore. It's a constant. This is the limit as x tends to infinity of the constant value 1, which is 1. So we would say, by the f of x trick, the limit as n tends to infinity, n over n plus 1, is 1. As another example, I'm going to look at the limit as n tends to infinity of a polynomial in n squared plus 3n plus 1, divided by e raised to the n power. The continuum function f of x is going to be x squared plus 3x plus 1 over e to the x. And again, I'm doing this because I can do things like L'Hopital's rule to it now. We've got an indeterminate form of type infinity over infinity again, so I'll take derivatives of the top and bottom. After doing that, I still have an indeterminate form of type infinity over infinity, so I'll do L'Hopital's rule again. I've got to stop doing L'Hopital's rule now because the top of the fraction is a constant, so I don't have an indeterminate form of type infinity over infinity anymore. In fact, I don't have any kind of indeterminate form at all. If I wanted to, I could rewrite the thing I'm taking the limit of as this. And remembering what the graph of y equals e to the minus x looks like, we can see that e to the minus x rapidly approaches 0 as x increases. 2 times something that's close to 0 is also close to 0. So this tells me that the limit as n tends to infinity, n squared plus 3n plus 1 over e to the n is actually 0. This says that the exponential function is getting bigger much more quickly than the quadratic function on top is. You can extend this argument to see that such a limit of any polynomial divided by an exponential function will also give you 0. Not every trick always works on a given problem, so we have to have a variety of them. The next one I want to look at is called the Squeeze Theorem. The premise for the Squeeze Theorem is that I'm going to have 3 sequences of numbers. I'll have the a_n numbers, the b_n numbers, and the c_n numbers. The presumption in the Squeeze Theorem is that the limit of these a sub n numbers is some actual number L. The limit of these cn numbers is that same number L, and the conclusion is that the limit of the b numbers is also that number L. This is not very hard to see. I'm just going to illustrate the idea with a picture. Using the idea that the c numbers are the biggest one out of the 3, and the a numbers are the smallest ones out of the 3, if I go to n equal 1, when I look at the a sequence, I'm going to have some y coordinate y equal a1, which has to be lower down than y equals c2, c1 that is, because of the inequality. Y equal a2 has to be lower down than y equals c2. Y equal a3 has to be lower than y equals c3, and so on and so forth. The remaining piece of the picture is that the b numbers are not in there any place. The b numbers are supposed to be between the a numbers and the c numbers. So, for example, if I were to draw in y equals b1, it might be there. If I were to draw in y equal b2, it might be there. Y equal b3 might be there. Y equal b4 might be there. And y equals c5 might be there. The key point is not whether the new dots are above or below the dotted line. The key point is that they're between the other pair of dots. So as you proceed off to the right, the amount of freedom that I have where I put this b number eventually gets squeezed out. B is between the a and c number for a given index, and the a and the c numbers are both approaching this number L, so the b numbers have to approach that as well. So this is a picture justification for this Squeeze Theorem thing. I want to think about this Squeeze Theorem in connection with this limit. Limit as n tends to infinity of e to the n over n factorial. the first thing you think of is, let's try L'Hopital's rule. Since the number on top, e to the n, and the number on the bottom, n factorial, both become arbitrarily big as you allow the n to increase, but there's going to be a problem with that. The top of the fraction is fine. E to the x is a function that becomes indefinitely big. It has a derivative equal to e to the x. Everything's nice. The problem is, the thing on the bottom is not anything we're familiar with. The only thing we know how to take factorials of are positive whole numbers and 0, and x might be 116.4. We have no way of doing that. To do this one, we're going to have to resort to algebra trickery. Remember what the factorial was. For instance, 5 factorial is the product of all positive whole numbers from 1 up to 5. I could write them in decreasing order, which is often done, or I could write them in increasing order. It makes no difference. The number of factors of e upstairs is n. The bottom of the fraction, n factorial, is the product of 1, 2, 3, all the way out to n. For each one of these e to the n over n factorials, the number of factors upstairs and the number of factors downstairs are the same. So I'm going to get some insight into this by splitting it up into factors. Before we do that, of course, I want to mention, obviously, all of these things are positive. E to the n over n factorial, all of them are positive. When n is 1, you'll only have one factor of n upstairs, and the single factor 1 being 1 factorial downstairs. When n is 2, upstairs you'll have e squared, and on the bottom you'll have 1 times 2, which is 2 factorial. I'll split that up into 2 fractions multiplied together. When n is 3, you'll have 3 factors of e upstairs, and 1 times 2 times 3 downstairs. Likewise for n equal 4, n equal 5, n equals 6, and if you have an n value that's bigger than 6, I can certainly represent the situation this way. Now, these numbers, e over 1 is about 2.7, e over 2 isn't much bigger than 1, e over 3 is actually less than 1, e over 4 is less than that, e over 5 is less than that, and e over 6, e itself is smaller than 3, so e over 6 is actually less than 1/2, and all subsequent factors will be even smaller than that. So I'm going to make up a name for this number. I'm just going to call it capital K. It's a constant. And then I have multiplied by e over 7 times e over 8 all the way out to e over n. In the original, I had n factors. I've split 6 of them off, so there are n minus 6 factors contained within the square brackets. So what this tells me is there's a constant k, so that e to the n over n factorial is trapped between 0 and this constant k multiplied by some power of 1/2. As you allow the n to become indefinitely big, the limit of a constant is the constant. The limit of a constant factor is the constant factor times the limit of the rest of it. As n tends to infinity, n minus 6 also tends to infinity. A large positive power of 1/2 tends to 0. So this tells me that must be true. And 0 less than or equal to the limit n tends to infinity, e to the n over n factorial has to be less than or equal to a constant times 0. We have put the squeeze on it now. There is only one number that obeys 0 is less than or equal to the number less than or equal to 0. This limit has to be 0. We found out earlier that exponential functions grow more quickly than polynomials. This new fact tells us that the factorial grows even more rapidly than the exponential one does, so this is a fact that's worth knowing. In Calculus 1, we had certain properties of limits. There are going to be similar properties for these new types of limits. So I'm going to presume that the limit as n tends to infinity of an is some actual number L, and the limit of the bn's is some actual number k. By actual number, I mean no inclusion of the infinity or negative infinity symbol for the L or k. Firstly, the limit of a constant times a function in this sense meaning sequence function, is the constant times the limit of the function. Secondly, the limit of the sum of two of these things is the sum of the individual limits. I've got to make a comment here. Both of those limits have to exist as actual numbers if this is to be true. If the limit of the an's and if the limit of the bn's converge to L and K respectively, then the limit of the sum is automatically guaranteed to converge to the number L plus the number K. The same is true if you're subtracting an minus bn. You would get L minus K in that case. The limit of the product of an bn is the product of the individual limits separately, assuming that they both exist. And the limit of the fraction an over bn is equal to L over K with some caveats. Firstly, you only look at bn's that are not 0, because otherwise you won't get an an over bn to talk about. And also, this only makes sense if k is not 0, so that L divided by k will be 0. These are the usual kind of properties of limits. This is what we have to work with if we want to do the usual limit manipulations. If I want to evaluate this limit, one way to do it is to make sure that the individual limits separately make sense, converge to an actual number, and then just add them together. I've got to be very careful about what I'm talking about, though. We've already seen that first limit a couple of different ways, so I'm just going to recall the result. The limit as n tends to infinity of n over n plus 1 is equal to 1. For the second one, we could do the f of x trick with f of x equal to 3x over x plus 5, or we could just do the algebra trick, which is what I'm actually going to do. I've got a linear polynomial in n upstairs, linear downstairs, so if I factor an n out and cancel, upstairs I'll just have the 3 left. Downstairs I'll have 1 plus 5 over n. When n becomes very big, 5 over n gets close to 0. The bottom of the fraction gets close to 1 plus 0, which is 1. The fraction gets close to 3 divided by 1. The fraction has a limit equal to 3. So having checked this, the limits of the two things individually both exist. That means it's legitimate to say that the limit as n tends to infinity, n over n plus 1 plus 3n over n plus 5. The limit of the first term exists and was 1. The limit of the second term exists and is 3. The limit that you're interested in exists and is 4. I want to look at a sequence whose individual terms are n plus 3 plus 1 over n, and also one whose terms are 5 minus n. If you look at the first one, the a numbers are n plus 3, which is positive, plus 1 over n, which is positive. So a number n is always going to be at least as big as n is. A number 10 is at least 10. A number 1,000 is at least 1,000. A number 1,000,000 is at least 1,000,000, and so on and so forth. By making the n big enough, I can make a sub n as big as I care to make it. So using the atrocious language that we've mentioned before, we would write limit as n tends to infinity of a n equals plus infinity, which, let me remind you, does not mean that there's some number that limit is equal to. That's shorthand for that limit doesn't even exist, and it doesn't exist in a certain particular way. Now, as far as the bn's go, imagine that n was 15. B number 15 is 5 minus 15, which is negative 10. Let n equal 105. B number 105 is 5 minus 105, which is negative 100. As far as the bn's go, 5 minus n will be negative when n is large enough, and by making n sufficiently large, you can make the bn as negative as you care to make it. So I think it's pretty clear that the limit as n tends to infinity of bn is negative infinity, meaning that that limit doesn't exist. And the way it doesn't exist is as you increase the index, the b sub n numbers become arbitrarily large in absolute value and negative. So let's think about the limit as n tends to infinity of an plus bn. If we don't understand what we've been doing, we automatically think it's the limit of the first thing plus the limit of the second thing. Presumably that would be the infinity symbol plus the negative infinity symbol. And then if we didn't know any better, we would say you take something and you add its negative, so you must get 0. This is wrong. This is completely wrong. Let me show you why. Limit n tends to infinity an plus bn. For each individual an, the value of n plus 3 plus 1 over n is a perfectly fine number. For each individual index n, bn, 5 minus n, is a perfectly good number. When I'm calculating the limit of an plus bn, I am calculating the limit of n plus 3 plus 1 over n plus 5 minus n. For each individual n number, an plus bn simplifies down to 8 plus 1 over n. 8's a constant term, its limit is 8. 1 over n tends to 0, as n tends to infinity. The limit of these two individual terms do both exist. The first limit is 8, the second limit is 0. The limit can be written as the sum of the individual limits. 8 plus 0 is 8. Doesn't this contradict what we said before? No, it doesn't. What we said before was, if the limit of the an's exist, which it doesn't in this case, and if the limit of the bn's exist, which it doesn't in this case, then I can write the limit of the sum as the sum of the limits, but the premise is not satisfied. The fact that these two things individually don't have limits doesn't necessarily mean that the sum doesn't have a limit. In this case, it does. In Chapter 9, Section 1, Sequences, there's one more thing that I want to talk about. This has to do with certain properties of sequences which will guarantee that they converge. I'm going to save that to the next discussion, so we'll pick this up there, either in the next meeting or in the next online discussion, and after that we will start talking about infinite series. I hope everyone's having a good day, and I'll talk to you again soon.